At the fifth step, we will estimate the CFA model parameters. The estimation procedures seek to minimize the discrepancies between the sample covariance matrix and the covariance matrix that is implied based on our theory. Essentially, we want to minimize the discrepancies between the S matrix and the sigma X matrix. There are two widely used fit functions. This includes the least squares fit function and the maximum likelihood fit function. With regression, we used the least squared fit function. CFA will use the maximum likelihood fit function. With the maximum likelihood fit function, the computer will solve the parameters iteratively. First, the computer will pick some initial estimates of the parameters, such as the lambdas, the covariance among the latent variables, and the error terms. Then the computers will compute the likelihood of data estimates. After computing the likelihood, the computer will try to improve the parameter estimate slightly and then recalculate the likelihood of the data estimates. The computer will do this over and over until we decide to stop. There are two strategies to stop. First, when the improvement is less than 0.01 or 0.001, we will say stop. Second, we can determine the number of iterations. We can tell the computer to stop after 20 iterations, or we can tell the computer to stop after 250 iterations. The likelihood of the parameter estimates is usually very small. We therefore will compute -2 likelihood. This is a measure of the likelihood of obtaining this observation. However, the -2 log likelihood is a badness of fit indicator. That is, larger numbers means per fit of the model to the data. When the -2 log likelihood is 0, then the model will fit the data perfectly. When we compare the target model with any of the alternative models, we will compute the chi-square. We will conduct the likelihood ratio test. That is the chi-square test. The chi-square test is the difference between the two models. One is the target model, the other one is the alternative model. We will compute the difference between the two values of -2 log likelihood. If the difference is significant, we will say that one model fits the data significantly better than the other model. After we have the result, we will determine the overall model fit. Basically, when a solution is converged, we will determine how well does the sigma X approximate the sample covariance matrix. As I mentioned, the chi-square represents a test of the badness of fit. A significant chi-square indicates that the theoretical covariance matrix differs from the sample covariance matrix. When making the decision based on chi-square, we face a dilemma. That is, with large samples, which is typical for CFA tests, mostly any model is likely to be statistically significant. Therefore, based on chi-square, we will not get a useful conclusions because most of the time chi-square is significant. Statisticians also developed other practical indices that help us to assess the model fit. There are 6 common indices. 4 are goodness of fit indices. In other words, the larger numbers will indicate a goodness of fit. These are NFI, TLI, CFI, and RNI. The criterion are CFI should be greater than NFI should be greater than 0.90, TLI should be greater than 0.90, CFI should be greater than 0.95, RNI should be equal or greater than 0.95. There are 2 indicators telling us the amount of errors. The first one is a standardized root mean residual, SRMR. This should be at or greater than 0.08. The second one is root mean squared error of approximation, RMC. This should be equal or less than 0.06. There are other fit issues, such as the admissibility of parameter estimates. The CFA solution should be good if all parameter estimates are within admissible ranges. However, sometimes, even though the model converged, we will have some inadmissible estimates, such as negative variance or standardized factor loading and factor intercorrelations are greater than 1. These are impossible values. When our output presents these values, it generally means that the solution is improper or the model is not plausible. There are some possible solutions, but Marsh warned that the improper solutions may signal that the model fit is inappropriate to the data. Therefore, we should not try to fix these inadmissible estimated models, but which actually need to look at the original direct model to see if there is any problem with the original model. Another fit issue is the parsimony of a model. That is, our model should be simple and parsimonious. When we have p number of items, the total parameters we can estimate equals to p multiply p plus 1 divided by 2. For example, when we have 4 items, the overall number of parameters we can estimate is 4 multiply 5 divided by 2, which is 10 parameters. If T is total number of estimated parameters, then the degree of freedom equals to total number of parameters minus T. In the above example, if we estimate 6 parameters, then degree of freedom equals to 10 minus 6, which is 4. Alternatively, if we estimate all 10 parameters, then degree of freedom equals to 10 minus 10, which is 1. When we have 0 degree of freedom, the CFA model will always fit the data perfectly. That is, we will estimate all parameters, nothing is fixed. The model will fit the data perfectly. We can always achieve a better fitting model by freeing up more parameters. However, if we need to estimate many number of parameters, this will run into the problem which is called over-parameterization. That is, our model needs to estimate everything. The model does not have any, is not that useful anymore because we are not predicting anything. We basically freely estimate all possible links among the items. Finally, we need to compare among alternative models. If a model B is nested within model A, it means that model B is a special case of model A. For example, if model A is a one-factor model, then model B is a two-factor model. Then model A is nested within model B. When one model is nested within another, we can compare if the one-factor model fits the data equally well as the two-factor model. The difference between the two nested models, model A with one factor and model B with two factors, can be evaluated as the difference between the model's chi-squares. That is, we compute the chi-square for model A, the one-factor model. We also compute the chi-square for model B, the two-factor model. Delta chi-square equals to chi-square B minus chi-square A, and delta degree of freedom equals to degree of freedom B minus degree of freedom A. With the chi-square degree of freedom, we can check if delta chi-square is significant. If it is significant, it means that the two-factor model fits the data significantly better than the one-factor model. In other words, we should retain the two-factor model and reject the one-factor model.